Okay guys, this is a quick video on the last problem from your Unit 4 test review packet. I know it says modified from the 2012 AB exam. I'm pretty sure this might just be the exact problem. I don't think we changed anything, or if we did, not much. This is number 3 from that year, so as a reminder, there's a lot of resources online, so if you wanted to look up this problem, you can find additional keys and probably some other teachers making some videos on it as well. So let's go through this real fast. It says, let f be the continuous function on the interval -4 to 3 whose graph consisting of 3 line segments and a semicircle centered at the origin is given above. Let g be the function given by this. So this is going to be a really important statement. And I'm actually going to just jump ahead really fast because a lot of times what we'll learn when we review at the end of the year is when you see a problem that starts like this, we're actually going to start by making a list right here. You'll notice in part B, it's going to ask you questions about G prime and G double prime. And if you look at part C and D, you'll also notice we're going to talk about horizontal tangent lines, which has to do with the derivative of G. Or down here, points of inflection, which have to do with the second derivative of G. It's helpful to start by just making a little list of how G relates to F, because even though our questions are all asking about G, what we actually have information about is F. So I'm going to go over here and just write, I already know that G of X is equal to the antiderivative from 1 to x of f of t dt. Well, since I know I need information about the derivative of g, I'm going to make a statement about how that relates to f. Well, if I take the derivative and antiderivative, we know to just plug in the bound that has an x term in it, so that's going to become f of x. Because it's in the upper bound, it's positive, and if I multiply by the derivative of x, I just have 1, so that doesn't change anything. We've also seen below that I'm going to need information about the second derivative of g. Well, if I take the derivative of each of these sides, I'm going to end up with f prime of x. So now I have this little box here, this little table of connections between G and F. And once I've made this statement once, I can start using these interchangeably in the rest of my problems because I've made a really clear statement about the relationship between G and F. So let's jump in. Okay, so part A says find the values of G of 2 and G of -2. So for G, I already have an expression for G, so I'm just plugging 2 in for X. Well, if I'm plugging it in for X here, this is the X term. We're not plugging it in for X. So G of 2 is the antiderivative from 1 to 2 of f of t dt. Now notice this graph just says the f is f. So this will work for both f of t and f of x. Okay. So this just wants the area under the curve from 1 till 2. Well, here's 1, here's 2. So they want this area here. Well, we unfortunately don't right now know what this point is, and knowing that y value is going to help me find the area of that triangle. So let's think about this real fast. You'll notice that as I go over 2, I go down 1. So as I go over 1, I should go down 1/2. So that point is going to be 2, -1/2. So if I want to find the area of this triangle, I'm going to have, it's below the x-axis, so it's going to be -1/2. Width is 1. The height of the triangle is 1/2. And if I want to simplify that, I'll get -1/4. But remember, you don't have to. You could leave it just like that. Okay, they also want me to find G of -2. That's going to be the antiderivative from 1 to -2. And you can already tell there's something a little wonky about this one because my bounds are switched. So if I'm going to find the area under the curve, the easiest thing is going to do is to switch this back to the normal direction so I can think about area above and below more normally. So what I really have is negative the area from -2 to 1 of f of t dt. So now I'm going to jump into finding the area. I'm going to throw that negative in front and apply it at the end. Now I want the area from -2 to 1. So here's -2 until 1. So I want the area of all of this. Now just to make this stand out a little bit compared to the part we did before, I'm going to throw a little red in here too. We're going to find the area of all of that. Okay, so let's find that area. This is above the x-axis, and it's a triangle, so it's going to be a positive 1/2, a width of 1, a height of 3. This is below the x-axis, so we're not going to add it, we're going to subtract it, and it's going to be 1/2 of a circle, so 1/2 of pi r squared. Now, we can leave our numerical answer like this, and I would leave it just like this, but if you did want to simplify, this is going to be 3/2, and that negative will get distributed to it. This is going to be 1/2 of pi, but it'll be negative plus pi over 2. So if you did want to simplify, that would be your answer, but you don't have to simplify like that. Okay, let's jump into part B. Now it says find G prime of 3. Now, the table that I made before is a little less visible, so I'm just going to rewrite it here so that I can see it for a little while. So I know that g of x is equal to the antiderivative of 1 of x, f of t dt. I know that g prime is equal to f, and I know that the second derivative is equal to the first derivative. Sorry, the second derivative of g is equal to the first derivative of f. So I'm just making that so we can still see it in the screen even though I've moved down a little bit. So the first thing we want is g prime of 3. Sorry, g prime of negative 3. And you'll notice, again, that my graph is about f, not about g. So how does this relate to f? Well, if we're doing g prime, that's equivalent to working with f. So really what they're asking for is f of negative 3. Well, that's just the function value. It's the output. So if I look up here and I go to negative 3, so negative 1, 2, 3, what's the output here? So let's take a look. As I go over 2, I went up 2. So as I go over 1, I'll go up 1 because this is a line. So what's the output at negative 3? It's 2. Now, in both of these problems we've just done, they've asked for 2 things each time. Make sure it's really clear what goes with. I know I didn't box g of 2 as part of my answer, but my equal signs make it very clear that this is equal to this, and then g of negative 2, this is my answer for that. Same thing here. I want to make it as clear as I can that 2 is my answer for this, and now I'm going to work separately on g double prime of negative 3. When we get ready for the AP exam, we really want to make sure we're communicating clearly, that the readers know exactly what you're leaving as your answer, and things like that. So now I want to know information about the second derivative. Well, we have that connection. The second derivative of g is equivalent to the first derivative of f. So really I just want f prime of negative 3. Well, wait a minute. If my graph is f and they want f prime, that's the slope of my graph at negative 3. So if I go up here, I want my slope here. Well, it's on a straight line, so I'm just doing rise over run. Rise is 2, run is 2, so my slope is 1. Again, because of my equal signs, it's clear that this answer goes with the second derivative. Okay, part C. Find the x-coordinate, so we don't need the full point, just the x-coordinate of each point, which the graph of g has a horizontal tangent line. Okay, for each of these points, determine whether g has a relative min, a relative max, or neither a min nor a max at the point. Justify your answer. So I'm going to have to write a sentence. So determine whether g has, so when I have a horizontal tangent line, that's often where I have my mins and maxes. So let's just draw some pictures real fast. Where g has a relative min would look like this. There's my minimum, my horizontal tangent line. A maximum. Or neither. Sometimes it can look something like this, where I have a horizontal tangent there just briefly, or it could be going down instead. But we need to figure this out. So let's start by just figuring out this thing about g has a horizontal tangent. Well, g has a horizontal tangent when its derivative is 0. Well, wait a minute. We're asking questions about g, but remember, my graph is information about f, so I need to connect this back to f. So g has a horizontal tangent when g prime is 0, or in other words, when f is 0. So let's go up here and look for that. Where is my output 0? Well, my output is 0 here. There's a value, a y value of 0, and here. So at x equals negative 1 and x equals 1. But we're not done with the problem. It asks me to figure out when do I have a relative min, a relative max, or neither. So if g has a relative minimum, that means its slope is changing from negative to positive, or g is going from decreasing to increasing. So let's think about this as that g prime again. So if g prime, so the slope would change from negative to positive. Well, if g prime is changing from negative to positive, that means that f is changing from negative to positive. So let's see if either of these are minimums. Am I changing from negative to positive? Nope. Am I changing from negative to positive? Nope. So let's try again. For a relative max, I'm changing from, so if g is increasing to decreasing, so g prime has, there's a positive slope, negative slope, so g prime is positive to negative, so I'm looking where f goes from positive to negative. Does that happen? Well, yeah, it happens here. Here my f value is positive, Here it's negative. So this is actually going to be a relative mass because my change for my derivative of g is going from positive to negative. If we look at this while we're still here, you'll notice this doesn't change from positive to negative or negative to positive. There's actually no sign change. It's going from decreasing to decreasing because the slope is negative to negative. So this one's going to be neither. This one's going to be a max. So let's see if we can write some sentences for that. I'm going to say g has a relative max at x equals -1 because f changed from positive to negative. Now, because my graph was f, I think the best thing to do is to use f as your justification, but because we've been really clear about the connection between f and g, if you'd also put because g prime changes from positive to negative, that would be fine. You could also even say because g changes from increasing to wait a minute, I'm scared I'm messing that up. G changes from increasing to decreasing, but I think the best thing to do is f because that's what my graph is. So here's my first one. It was at -1. We also had a horizontal tangent at 1, but we're going to say g has neither a min nor a max at x equals 1 because f prime of x did not change signs. Okay. So remember, it asked for the places that had a horizontal tangent. We looked for where the derivative of g was 0, or in other words, where f was 0. So those are my places, and then we checked for each one if it was a min, a max, or neither. Okay, so now let's jump into part D. On my interval from -4 to 3, find all values of x for which the graph of g has a point of inflection. Explain your reasoning. Okay, so we're looking for a point of inflection. Now, often when we look for it algebraically, we're solving for the second derivative either being 0 or undefined, but the easier thing to think about for a point of inflection is we actually have to have a sign change for the second derivative. So I want to know where the second derivative of g changes signs. Okay? Remember, my graph isn't g, my graph has information about f, so I need to change this into an f statement. So the second derivative of g, you can see it right here, is the first derivative of f. So if I want where the second derivative changes signs for g, I'm looking for where the first derivative of f changes signs. Okay. Well, if I'm also looking, the way I can think about this, if I'm thinking about where the derivative of f is changing signs, so when f is when the derivative is positive to negative, if the derivative is positive, that means my slope is positive, I'm increasing. So another way to think about this is f changes from increasing to decreasing or decreasing to increasing. Now, I wouldn't necessarily use this when I write my justification in a moment, but just for right now to help us think about it, I can look for a change in increasing to decreasing. So I'm going to do that. I'm going to look for where does f change from increasing to decreasing or decreasing to increasing. Well, here it does. I went from increasing to decreasing. Here I went from decreasing to increasing. And here I went from increasing to decreasing. Or in other words, I changed my slope changed from positive to negative, negative to positive, or positive to negative. So let's go down here and write it. I'm going to say that g has POIs at x equals -2, 0, and 1 because we said f changed from increasing to decreasing or decreasing to increasing. Pen's starting to die a little bit. Okay, we also could have said this. We could have said because f prime changed from positive to negative or negative to positive. That also would have been a good answer. Okay, so I hope that was helpful. I'll see you guys soon for your test.